Apophis 2029. On the 13th of April in 2029, a piece of stone and metal about 370 meters across will sweep past the Earth at a distance closer than the orbits of geostationary satellites. The object is called Apophis. For a few hours it will become bright enough to see with the unaided eye, a moving point of light tracking against the stars above parts of Africa, Europe, and the Middle East. Apophis was discovered in 2004. Early calculations suggested a worrying chance of impact in 2029 or 2036. Subsequent observations narrowed the orbit and ruled out collision for at least the next century. The body will not hit. But the distance, around 32,000 kilometers above the surface, is the closest pass of an asteroid this large that humans have ever been able to predict in advance. The flyby has become a major event in planetary science. NASA's OSIRIS-APEX mission, a renamed and redirected probe, is already on its way to rendezvous with Apophis just after the close approach. The European Space Agency and other groups have proposed additional craft. The encounter is expected to reshape the surface of the asteroid through tidal stress, providing a rare laboratory for how small bodies respond to planetary gravity. For viewers on the ground, the experience will be quiet but unprecedented. Most people who look up that night will not bother. Those who do will be watching, with their own eyes, an object the size of a small mountain pass, close enough that, in a different orbit, it could have ended a city. The event will be over within a few hours. The dot of light will fade into the deep sky and continue on its long journey around the sun. Magnetic flip. The Earth's magnetic field is generated by the motion of molten iron in the planet's outer core. The field has a roughly north-south axis at the surface, but the pattern is not fixed. Over geological time, the field weakens, scrambles, and reverses. The compass needles that today point toward the Arctic would then point toward Antarctica. The last full reversal happened about 780,000 years ago. The geological record shows that reversals are irregular and unpredictable. They occur on average every 200 to 300,000 years, but with long gaps and short bursts. The current interval, nearly 800,000 years and counting, is unusually long. The field has been weakening for the past 200 years, dropping by about 9% of its strength globally. Over the South Atlantic, the field is particularly weak. A reversal does not happen overnight. The transition takes thousands of years, during which the dipole field weakens and may temporarily develop multiple poles in unusual places. Compasses become unreliable. Cosmic rays and solar particles, normally deflected by the field, reach further into the atmosphere and cause higher radiation at high altitudes. Satellites become more vulnerable. The aurora may appear at latitudes where it has not been seen for generations. The Earth and its life have survived many such transitions. The fossil record shows no mass extinction associated with reversals. The technological consequences in a modern civilization, however, are largely untested. The next reversal may already be underway, slow enough to be invisible in any human lifetime, fast enough to surprise the engineers responsible for power grids and navigation systems several centuries from now. The compass on the wall today is being quietly outvoted from below. ISS falls. The International Space Station has been continuously inhabited since November of 2000. It is the largest object humans have ever placed in orbit, with a mass of about 420,000 kilograms, and it is the third brightest object in the night sky after the Moon and Venus. Aging hardware, repeated micrometeoroid impacts, and the limits of its maintenance window mean it cannot stay up forever. The agencies involved have agreed to retire it. In January of 2031, the planned end of operations will arrive. The station will be commanded into a controlled descent. SpaceX has been contracted to provide a specially designed deorbit vehicle. The craft will dock with the station, fire its engines, and gradually lower the orbit until the structure encounters thicker atmosphere. As it descends, the great solar panels and external structures will break off first. The pressurized modules will follow, glowing as they fall. Most of the station will burn up. The pieces that survive, including denser metal components, will splash down in a remote part of the South Pacific known as Point Nemo, the spacecraft cemetery used for decades to retire large orbital objects. The debris field will stretch for thousands of kilometers. The whole event, from undocking to splash, will take a few hours. The fall will be visible from much of the world. Witnesses below the descent path will see a long bright streak across the sky, larger and brighter than any re-entry yet recorded. The space station that has hosted hundreds of astronauts and orbited the planet every 90 minutes for over 3 decades will arrive on Earth at last as the largest object ever to deliberately fall from orbit in a single coordinated dive into the empty sea. Time overflow. Inside many of the world's computer systems, the current date is stored as a single number, the count of seconds since the 1st of January in 1970. The format is called Unix time. It was chosen in the early days of computing when memory was scarce and a 32-bit signed integer was generous. That integer can count up to a value of around 2,147,000,000. That value will be reached at 3:14 in the morning, Coordinated Universal Time, on the 19th of January in 2038. At that exact second, a 32-bit signed Unix counter will overflow. It will roll from its maximum positive value to its maximum negative value, jumping in an instant from the present into roughly 1901. Any system that depends on the counter will misbehave in surprising ways. The scope of the problem is harder to estimate than the famous year 2000 bug. That one affected mostly desktop computers and mainframes, which were upgraded in plain sight. The 2038 problem affects embedded systems, the small chips inside power grid controllers, factory equipment, medical devices, banking backends, and ships. Many of those chips will still be running in 2038, often in places nobody has thought to inspect. Newer systems use 64-bit time, which pushes the next overflow far past the heat death of the sun. The fix is well known. The work of applying it everywhere before the deadline arrives is uneven and incomplete. Somewhere in some forgotten room, a counter is already heading for the cliff, and the people responsible for it have probably retired or moved on without noticing. Dead Sea dies. The Dead Sea sits at the lowest land elevation on Earth, in a deep rift valley between Israel, Jordan, and the West Bank. Its waters are nearly 10 times saltier than the ocean, dense enough that swimmers float without effort. The basin has been a single closed system for millions of years, fed by the Jordan River and a few smaller tributaries, with no outlet except evaporation. The Dead Sea is now shrinking. Diversions of the Jordan River for agriculture and drinking water, combined with mineral extraction at the southern end and the natural pressure of evaporation in a hot desert, have caused the water level to drop by more than 30 meters since the 1970s. The shoreline is retreating by about a meter each year. Thousands of sinkholes have opened in the exposed ground around the receding shore, swallowing roads, parking lots, and farms. Without significant intervention, the Dead Sea will continue to shrink, eventually becoming 2 small ponds at the north and south ends, separated by dry salt flats. Some estimates suggest the larger northern basin could still persist for centuries in a much reduced form, while the shallower south will dry first. Either way, the body of water that has appeared in maps, scriptures, and travel accounts for thousands of years will be a much smaller and less recognizable feature. Proposed rescue projects have included pipelines from the Red Sea or the Mediterranean to refill the basin. The engineering is feasible. The political coordination across the three governments that share the shoreline has been difficult. For the moment, the sea continues its retreat, the sinkholes continue to open, and the lowest place on Earth keeps falling, slowly, toward a future where the water that gave it its name is mostly gone. Sky garbage. In 1978, the American astrophysicist Donald Kessler proposed a scenario in which the density of objects in low Earth orbit grows so high that collisions between them become routine. Each collision creates more debris. The new debris causes more collisions. Eventually, certain orbital altitudes become a self-sustaining cloud of fragments, impossible to traverse safely. The scenario is now known as Kessler syndrome. The scenario was theoretical when Kessler proposed it. It is no longer. The number of tracked objects in orbit has increased from a few hundred in the 1960s to over 30,000 today, with millions of smaller untracked pieces. Several real collisions and intentional satellite destruction events have already added clouds of debris. The 2009 collision between the Iridium-33 satellite and a defunct Russian Cosmos satellite was, on its own, the worst commercial debris event in history. A worsening Kessler scenario would jeopardize the routine use of space. Communication satellites, weather monitoring, GPS positioning, scientific research, and the human presence in orbit all depend on relatively clean access to specific altitudes. If debris density in those altitudes climbs past a tipping point, the cost of every launch rises sharply, and some orbits become permanently unusable. The Earth would have, in effect, a permanent ring of rubble at the height where most modern technology lives. Mitigation efforts exist. Several companies and agencies are developing methods to remove dead satellites, capture debris fragments, and design new spacecraft that deorbit themselves at the end of their lives. Whether these measures arrive at scale before the syndrome accelerates is uncertain. A few more bad collisions could trigger the cascade. The sky above us, normally invisible at orbital altitudes, has been quietly filling with the metal we have left behind. Mercury chaos. The orbits of the planets in the solar system are usually presented as stable circles, each planet moving along its own ellipse for billions of years. The presentation is approximately correct over short timescales. Over very long timescales, however, the orbits interact with one another in subtle and chaotic ways. Small gravitational tugs accumulate. Over hundreds of millions of years, predictions become unreliable. Mercury is the smallest of the inner planets, and the one most affected by chaos. The geometry of its orbit makes it especially sensitive to nudges from Jupiter. Long simulations of the solar system show that Mercury's orbit can grow more elongated over time, with a small but real probability of becoming unstable enough to cross the orbits of Venus, Earth, or Mars. The simulations disagree on the exact outcome, because chaos amplifies tiny differences in initial conditions. In a small fraction of simulated cases, Mercury collides with Venus, Earth, or the Sun within the next 5 billion years. The figure, around 1% in most studies, is small, but not zero. The implications of a planetary collision in the inner solar system would be cataclysmic. A merger of Mercury and Venus would reshape both planets. A near pass to Earth could destabilize our own orbit, with severe consequences for the climate and for life. This is one of the few open questions in classical mechanics where the long-term answer is genuinely uncertain. The chaos is intrinsic to the geometry of the system, not a result of measurement error. The risk is not imminent in any human sense, but the elegance of the solar system as a permanent clockwork is, mathematically speaking, an illusion. The planets are slowly rolling dice with one another, and one of the dice has the smallest planet on it. Africa splits. In the eastern part of the African continent, a great fault system called the East African Rift is slowly pulling the land apart. The rift runs for roughly 6,000 kilometers from the Red Sea in the north through Ethiopia, Kenya, and Tanzania, ending in Mozambique. Along this line, the Somali plate is splitting from the larger Nubian plate. The rate of movement is small in human terms, about 0.5 centimetre to 1 centimetre a year, but the geology is unambiguous. Over time, the rift will widen. Surface evidence is already dramatic. In 2005, a large crack tens of meters wide opened in the Ethiopian desert in a single sequence of dike intrusions. In 2018, another fissure suddenly appeared in the Suswa area of Kenya, swallowing roads and farms. These are the visible scars of the slow continental break. Volcanoes along the rift, including Kilimanjaro and Nyiragongo, are themselves products of the same separation. In 10 million years or so, the rift will widen enough to be flooded by seawater from the north. A new ocean basin will appear between the two halves of Africa, similar in form to the early Red Sea or the original Atlantic. The Horn of Africa will become a large island, drifting slowly east. The new sea will eventually be among the largest on Earth, with its own coastlines, its own ecosystems, and its own weather. The change is well outside any human lifetime, but the process is already in motion. The map of Africa in the 21st century shows a continent whose eastern edge is, in the deep geological sense, in the slow process of falling off. The crack runs through populated land. The forces driving it are the same forces that opened the Atlantic and shaped every major ocean basin on the planet. Next ice age. For the last 2.5 million years, the Earth has been in a long period of alternating cold and warm climates called the Pleistocene and Holocene epochs. Glacial periods, when ice sheets covered large parts of North America and Northern Europe, have been interrupted by shorter warm periods called interglacials, when most of the ice retreated. We are currently in an interglacial that began about 11,000 years ago. The pattern is driven by slow changes in the Earth's orbit and tilt, known as the Milankovitch cycles. Over periods of tens of thousands of years, the geometry of the planet's orbit alters the amount of summer sunlight reaching the high northern latitudes. When summer sunlight drops below a certain threshold, snow accumulates from year to year, ice sheets grow, and the climate cools globally. The pattern has been remarkably regular for the last million years. Based on the orbital calculations alone, the next glacial period was expected to begin within the next several thousand years. Several papers in the early 2000s suggested that natural factors had set the stage for a relatively cold interglacial, with mild cooling already due. Human-caused carbon dioxide emissions have changed the picture sharply. The current concentration of carbon dioxide in the atmosphere is higher than at any point in at least the last 800,000 years, and the warming this produces overwhelms the orbital cooling. Modern climate models project that the next glaciation has been postponed by tens of thousands, or even hundreds of thousands of years. The carbon dioxide added to the atmosphere will not be removed naturally on any short timescale. The next ice age, scheduled by the orbital cycle, has been pushed back by human industry. The cycle itself will resume eventually. The mile-thick sheet that once buried Chicago has only been delayed. Longer day. The Earth's day is slowly lengthening. The rotation of the planet is being braked by tidal interactions with the Moon. As the Earth spins, the gravitational pull of the Moon raises tides not only in the oceans, but in the solid rock. The bulge of water and rock under the Moon's pull leads the Moon slightly in the direction of Earth's rotation. The misalignment exerts a tiny drag on the planet's spin, slowing it by a small fraction of a second per century. The slowing is measurable. Records of ancient eclipses, observed by Babylonian and Chinese astronomers, can be compared to the position the same eclipses would have appeared in the sky if the day had not changed. The discrepancy shows that the day has lengthened by a few seconds since antiquity. Modern atomic clocks measure the change more precisely. The day grows longer by about 1.7 milliseconds per century. Projected forward over very long periods, the change becomes substantial. Around 200 million years from now, the day will be roughly 25 hours long. The change will be invisible to anyone living through it, but it will reshape biology, ocean tides, and the patterns of climate. Life that depends on 24-hour cycles, from circadian rhythms in animals to flowering schedules, will quietly adapt to the new pace. The Moon is also drifting away as it borrows angular momentum from the Earth's spin. Both processes are linked. Eventually, billions of years from now, the Earth's day and the Moon's orbit will lock into a synchronous rotation, with both bodies always showing the same face. The pace will continue to slow slightly every century. The day on your watch is one tiny fraction of a second, too short to last forever. Vacuum decay. The universe might rest on a setting that is not, technically, the lowest possible energy state. Quantum field theory describes the vacuum of empty space as a sea of fields. Most models assume our current vacuum is the deepest valley, the state to which everything settles. A minority of models, supported by precise measurements of the Higgs field and the top quark mass, suggest that the valley we sit in could be a metastable plateau with a deeper one below. If such a deeper valley exists, the universe is one rare quantum event away from beginning to fall toward it. The event would be the spontaneous formation of a tiny region where the vacuum slips into the lower state. The new region would expand outward at very close to the speed of light, replacing the old vacuum with the new one, and rewriting the laws of physics inside the expanding sphere as it went. The boundary of that sphere would travel faster than any signal could outrun. No warning would reach the future location of the bubble. From inside an unaffected region, the night sky would look normal until the moment of replacement, at which point everything in line of sight would already have been swapped. Nothing the inhabitants could do would prepare them. They would simply, suddenly, cease to exist along with the laws that had supported them. Current measurements place our vacuum on the edge between stable and metastable. The expected lifetime of a metastable vacuum, if it is metastable, is calculated as longer than the present age of the universe by many orders of magnitude. The event might not occur for 100 trillion years, or it might occur in the next second. Astronomers cannot detect a bubble forming somewhere distant. There is no way to know. Banana extinction. The banana most people eat is a single variety. The Cavendish, grown in plantations from Ecuador to the Philippines, is genetically nearly identical from one fruit to the next, propagated by cuttings rather than seeds. The variety became dominant in the 1960s after a fungal disease called Panama disease wiped out the previous market leader, the Gros Michel. A new strain of the same disease, called Tropical Race 4, has now spread across most of the world's banana-growing regions. It attacks the Cavendish with the same lethal efficiency it used on the Gros Michel. Once the fungus enters the soil of a plantation, the soil itself becomes uninhabitable for the banana, often for decades. Land that goes infected stays infected. Replanting is not an option. Because the global banana trade depends on this single clone, the disease threatens the entire industry. Researchers in several countries are working on resistant varieties, including genetically modified Cavendish lines, that have shown promising results in field trials. Wild banana species, found mostly in Asia, hold genes that could be crossbred into commercial varieties. None of these solutions are yet at scale. The most likely outcome is that the Cavendish, as a globally traded fruit, slowly disappears from supermarkets. Some replacement variety, with a different flavor and texture, will take its place. Older shoppers will remember the original taste the way an earlier generation remembered the lost Gros Michel, whose flavor, according to those who tasted it, was richer and sweeter than the bananas in shops today. The fruit on the shelf is on a slow, irreversible march towards something else. Tonight's nova. In the constellation Corona Borealis, a faint binary star system called T Coronae Borealis has been on the verge of a spectacular outburst for several years. The system consists of a small, dense white dwarf and a larger red giant, locked in close orbit. Gas from the red giant slowly streams onto the surface of the white dwarf, where it accumulates over decades until pressure and temperature trigger a runaway nuclear reaction in the borrowed fuel. When the reaction begins, the surface of the white dwarf erupts in a sudden flash of light, brightening the system by a factor of more than 1,000 within hours. From Earth, the dim star, normally invisible to the naked eye, will appear as a new point in the sky, similar in brightness to the North Star. The eruption is called a nova. T Coronae Borealis is recurring, repeating its outburst roughly every 80 years. Records of past eruptions exist from 1866 and 1946. Based on the pattern, astronomers expected the next outburst sometime between 2024 and 2025. The actual moment has been delayed. Observers around the world monitor the system nightly, waiting for the first sign of brightening. Once the light reaches Earth, the event will be visible to anyone in the Northern Hemisphere with a clear sky. The outburst is not a true supernova. The white dwarf survives. The cycle of accumulation and ignition continues. A new generation will witness the brightening that the previous generation, in 1946, also stayed up to watch. Somewhere between this paragraph and the next 80 years, the nova will arrive on a particular ordinary night, and the constellation will briefly hold a star that was not there before. Mississippi Escape. For thousands of years, the Mississippi River has wandered across the southern Louisiana floodplain, choosing new paths to the Gulf of Mexico every few centuries. The current channel, which runs through the city of New Orleans and continues to the sea, is a relatively recent route. The river prefers, by basic hydraulic logic, to abandon it. A steeper, faster path is available about 50 kilometers to the west, through the Atchafalaya Basin. The river has been trying to make the switch for decades. By the 1950s, the volume of water leaking from the Mississippi into the Atchafalaya had grown large enough to threaten an uncontrolled change in course. The United States Army Corps of Engineers built a series of structures called the Old River Control Complex to hold the split at a fixed ratio. Roughly 70% of the combined flow continues down the Mississippi, and 30% goes through the Atchafalaya. The decision is not made by the river. It is made by concrete. If the structures fail, the river will switch overnight. The Mississippi past New Orleans will drop to a trickle. The port of South Louisiana, one of the busiest in the world, will be cut off from ocean-going ships. The refineries and chemical plants along the lower river depend on the current flow for cooling water and shipping. New Orleans will lose its drinking water intakes and its river-based economy in a single season. Each major flood places additional stress on the control complex. The structures have already required emergency repairs. The Corps engineers know that the river will eventually win. The only question is whether the switch happens slowly, with time to prepare, or in a single flood event that arrives before any plan is in place. The water has been waiting patiently to leave. Q-Day. Modern encryption depends on mathematical problems that classical computers cannot solve in a reasonable amount of time. Internet traffic, banking, military communications, and private messages are all protected by algorithms that would take a regular computer billions of years to break. The security rests on the difficulty of certain operations, particularly factoring very large numbers and computing discrete logarithms. Quantum computers do not face the same limits. An algorithm developed by Peter Shor in 1994 shows that a sufficiently large and stable quantum computer could factor enormous numbers in hours instead of geological ages. The same algorithm cracks the discrete logarithm problem. Together, these two breakthroughs would render most current encryption schemes immediately obsolete. The day this becomes practical is called Q-Day. No quantum computer has yet reached the scale required. Current machines have a few hundred to a few thousand noisy qubits. Breaking standard encryption would require several million stable logical qubits, which in turn would require even more physical qubits with error correction. The timeline is debated. Some researchers expect a decade or two. Others see fundamental obstacles that may never be overcome. The hardware is improving steadily either way. The risk is not only future communication. Sensitive material being transmitted today, including state secrets, medical records, and financial data, is being harvested and stored by various governments under the assumption that it can be decrypted later when Q-Day arrives. Anything currently encrypted that should still be private in 20 or 30 years is, in effect, already at risk. National standards bodies are quietly rolling out new post-quantum algorithms designed to resist the attack. Humanity shrinks. For most of recorded history, the human population grew. The growth was slow for thousands of years, then accelerated dramatically after the Industrial Revolution. By 2024, the global total had reached around 8 billion. The standard projection used to assume the curve would continue rising, peaking somewhere above 10 billion by the end of the century, before leveling off. The projection has been revised downward. Fertility rates have fallen faster than demographers expected in nearly every country with reliable data. The number of children born per woman, averaged globally, has dropped from around 5 in the 1960s to around 2.3 today. The number considered necessary to maintain a stable population in modern conditions is about 2.1. The world average is now barely above replacement. In some regions, the decline is much steeper. South Korea, Japan, much of Southern Europe, China, and increasingly the United States are seeing fertility rates well below replacement, with no sign of recovery. As these populations age, deaths begin to outnumber births. Without immigration, the country shrinks. The total global population is now expected to peak somewhere in the 2060s, perhaps as low as 9.4 billion, then begin to decline. This will be a new experience for the species. No civilization in human history has voluntarily shrunk over many generations. The economic models, the pension systems, the housing stock, The political assumptions of the modern world are built for a growing population. None of them have been tested under sustained decline. Within the lifetime of someone alive today, the human total will start to fall, slowly at first, then perhaps faster, for the first time since the bubonic plague. Betelgeuse explodes. In the constellation Orion, the bright red star Betelgeuse marks the hunter's left shoulder. It is one of the largest known stars in the galaxy, with a diameter that would extend past the orbit of Jupiter if it sat where our Sun does. It is also nearing the end of its life. Betelgeuse will explode as a supernova. The question is only when. The current age of Betelgeuse is estimated at around 10 million years. Very young for a star, but extreme for one of its mass. Massive stars burn through their fuel quickly. After the final phases of fusion, when iron accumulates in the core, the structure collapses inward and rebounds in an explosion that briefly outshines all the other stars in the galaxy combined. The visible light reaches Earth in the form of a supernova, leaving behind a neutron star or a black hole. When Betelgeuse explodes, viewers on Earth will see something humans have not seen in over 400 years. The supernova will be bright enough to read by at night and visible during the day. It will dominate the sky for weeks before slowly fading. There will be no danger. Betelgeuse is around 650 light-years away, far too distant for the explosion to threaten the solar system. It would be a spectacle, not a catastrophe. The exact timing is unknown. Models suggest the event could happen any time within the next 100,000 years. By cosmic standards, that is the next instant. Light from the explosion is already on its way, possibly partway here. The flash arriving at Earth tonight, or in 20,000 years, will look the same. Astronomers can only watch and wait, knowing that the star already exploded long ago, and the news is still in flight. Antibiotics die. Antibiotics changed medicine. Before they existed, a simple infection from a scratch or a routine surgery could kill. After the discovery of penicillin in 1928 and the wave of new drugs that followed, infections that had been common causes of death became routine to treat. Modern surgery, chemotherapy, organ transplants, and most intensive care depend on the ability to control infection with reliable drugs. Bacteria do not stand still. Every dose of an antibiotic exerts selection pressure on the bacterial population, favoring any individual that happens to carry a mutation, reducing the drug's effectiveness. Resistant strains spread, sometimes carrying the same resistance to other related drugs. The history of antibiotics, from the start, has been a race between the introduction of new drugs and the evolution of resistance to old ones. The race is now being lost. Several types of bacteria, including some forms of tuberculosis, gonorrhea, and certain hospital strains of E. coli, are resistant to nearly every drug available. The pipeline for new antibiotics is thin, partly because of scientific difficulty, and partly because the drugs are not profitable enough to interest most large pharmaceutical companies. Each year, around 1.25 million people are estimated to die from infections that would have been treatable a generation ago. If the trend continues without major intervention, the world will move into a post-antibiotic era. The surgeries we now consider routine will become dangerous again. The cancer treatments that suppress the immune system will be too risky to use widely. The everyday infections will return to killing the very young and the very old. The drugs are still in the cabinet. They simply will not work the way they did when they were new. Solar storm. In September of 1859, a massive solar flare struck the Earth. The event, named the Carrington event after the astronomer who first observed it, charged the atmosphere with enough electrical current to set telegraph wires on fire and let operators communicate without connected batteries. Auroras were seen as far south as the Caribbean. The Earth had its electrical systems, such as they were, briefly overwhelmed by the sun. A similar event today would be far more disruptive. Modern civilization depends on a vast network of transformers, communication satellites, power grids, and fiber optic cables. Most of these systems were designed to handle the level of solar activity that has occurred during the satellite age, which is well below a Carrington-class event. A direct hit from a comparable flare would damage transformers across entire continents, with replacement times measured in years rather than weeks. The sun is known to produce these events. Tree rings, ice cores, and ancient bristlecone pinewood have preserved evidence of multiple extreme solar storms over the past few millennia, including events larger than Carrington. Several near misses have occurred in the satellite age. In 2012, a Carrington-class coronal mass ejection passed through the orbit of Earth, but the planet had moved past that point in space a few days earlier. Forecasts of solar weather have improved, but the warning time before a major event would be measured in hours, not days. Grid operators could disconnect transformers to protect them at the cost of widespread blackouts. The internet, banking, refrigeration, and most of modern life would pause for an extended period. The sun has been the source of every problem the Earth has ever solved, and one of these solar storms is overdue. Last century born, somewhere on Earth today, a baby was born in 2024 or 2025, who statistically has a reasonable chance of becoming the last person alive who was born in the 1900s, the 20th century, by calendar count. The cutoff date is the 31st of December in 1999. Anyone born on or before that date was born in the 20th century. The youngest such person, at the moment of this writing, is about 25 years old. Human life expectancy in wealthy countries currently averages around 80 years for men and 84 for women. A small fraction of any cohort lives well past that. The longest verified lifespan on record is 122 years, achieved by Jeanne Calment of France. Most cohorts produce at least one supercentenarian, someone living past 110. If even one such person from the late 1900s reaches that age, the last 20th century human will outlive the year 2100. The probability of any specific individual being the very last is vanishingly small. The probability that someone eventually will be the last is 1. That person is alive right now, somewhere, probably finishing school, possibly already working, almost certainly unaware of the small statistical distinction they carry. The cohort of 20th century humans is now closing. No new members can join. Their eventual death will mark a small but real demographic boundary. The 20th century, the period of 2 world wars, decolonization, the rise of the internet, the moon landings, will pass entirely from living memory. Anyone who claims to have been there will be wrong. The witnesses will be gone. The century itself will become, like every century before, a thing remembered through writing and recordings, with nobody left who saw it firsthand. Yellowstone erupts. Beneath the geyser fields and hot springs of Yellowstone National Park sits one of the largest volcanic systems on the planet. The Yellowstone caldera is about 72 kilometers long and 55 kilometers wide, the remnant of 3 enormous eruptions over the past 2 million years. The most recent of these, 640,000 years ago, ejected around 1,000 cubic kilometers of ash and rock and left the modern caldera behind. A future eruption on the same scale is possible. The magma chamber beneath the park is still active, slowly heating, ringed by faults. Smaller eruptions, including lava flows and hydrothermal explosions, have occurred more recently. The threshold for a supervolcanic eruption, however, requires a specific buildup of pressure and gas that is not currently in progress. The United States Geological Survey monitors the caldera continuously and has detected no signs of an imminent major event. If a super eruption did occur, the consequences would extend far beyond the park. Ash falls would bury several states under meters of debris, collapsing roofs and killing crops. Sulfur and dust injected into the upper atmosphere would lower global temperatures by several degrees for years afterward, similar to the so-called year without a summer that followed the Tambora eruption in 1816, but on a far larger scale. Global agriculture would fail. Famine would follow. The likelihood of such an event in any given century remains low. Yellowstone has erupted on average once every 600,000 years, and we are now beyond that average gap. The volcano is not on a schedule. It is, however, capable of producing the largest disaster modern humans have ever faced, on a timetable that could be next year or 200,000 years from now, with the difference invisible to anyone watching. Halley returns. Halley's comet is the only short-period comet bright enough to be seen reliably with the naked eye, and the only one whose return any individual can hope to witness twice in a lifetime. It follows an elliptical orbit that brings it close to the Sun roughly every 76 years. Records of its appearances stretch back to at least 240 before the Common Era, when Chinese astronomers noted it in their observations. The comet was last seen from Earth in 1986. The encounter was a disappointment. The geometry of the approach kept it far from Earth at its brightest, and the comet itself was less spectacular than expected. Several spacecraft, including the European Giotto probe, flew close to the nucleus and confirmed it as a dark, irregular block of ice and dust, about 15 kilometers long, releasing gas as it approached the Sun. The next return is calculated for late July of 2061. The geometry this time is more favorable. The comet should pass closer to Earth on the inbound leg of its orbit and be far brighter than in the 1986 approach. The tail should stretch across a substantial portion of the sky. A whole generation will see it without binoculars or telescopes. Some readers of this paragraph have already seen it once and will see it again. Halley itself loses a thin layer of material with each passage near the Sun. After many thousands more orbits, it will eventually disintegrate, breaking into a stream of fragments. For now, the body is still substantial, still on schedule, still due to round the inner solar system in 2061. The night sky will hold the comet for several weeks. The next return after that, in the late 2100s, will belong to other people entirely. Digital Dark Age. In 1945, a photograph taken with a film camera could still be developed 80 years later if the negative was kept dry. The chemistry was simple and stable, and the image could be retrieved with no specialized equipment. Modern photographs and documents are different. They are stored as digital files in formats that depend on specific software, specific hardware, and specific storage media. The combination is far less durable than people assume. Hard drives fail. Solid-state drives slowly lose their charge if left unpowered. Optical disks delaminate within decades. Cloud services close, lose contracts, or simply discontinue old file formats. Even when the bits are preserved, the software needed to read them often disappears. Old proprietary file formats, the early word processors and image programs of the 1980s and 90s, are already mostly unreadable without specialist effort. The internet is similarly fragile. A typical web page survives for about 100 days before being changed or removed entirely. The links pointing to it slowly rot as the cited pages move or vanish. The Internet Archive saves some of this content, but only a small fraction of the whole. The shared global memory of humanity in the 1990s, the early years of the public web, is now a patchwork of broken links. The danger is a quiet one. Photographs of weddings, scientific data, financial records, family videos, and the entire creative output of the early digital era are all at risk. Future historians may know less about the first century of digital culture than they know about ancient Rome. The records exist. They simply will not be readable. Civilization has, for the moment, traded the certainty of paper for the convenience of bits, and the cost has not yet been paid. Ocean conveyor. The Atlantic Ocean has a vast circulation pattern called the Atlantic Meridional Overturning Circulation, or AMOC. Warm surface water flows northward from the tropics toward the polar regions. There it cools, becomes denser, and sinks to the deep ocean, where it begins a long journey southward. The sinking is concentrated in the seas near Greenland and Iceland. The pattern moves enormous amounts of heat and shapes the climate of much of the northern hemisphere. The AMOC is sensitive to fresh water. Melting Greenland ice and increased rainfall in the North Atlantic dilute the surface salinity. Less dense water resists sinking, which slows the entire circulation. Direct measurements over the last 2 decades, along with proxy records from the past 2,000 years, suggest the AMOC has weakened to its slowest pace in over 1,000 years. A complete shutdown is possible. Models disagree on how close the system is to a tipping point, but the disagreement is mostly about timing, not about the existence of the threshold. If the circulation collapses, the consequences would be severe and rapid. Northern Europe could cool sharply within decades, even as the rest of the globe continues to warm. The tropical rain belts that depend on the heat transport would shift, drying the African and South American monsoon regions. Sea levels along the eastern coast of North America would rise faster. Recent papers have placed the possible shutdown anywhere from the next few decades to a century or two from now. The uncertainty is large enough that careful scientists hesitate to put a number on it. But the freshwater inputs are increasing, the salinity is dropping, and the circulation is slowing. The conveyor that keeps Britain warmer than Labrador, despite both sitting at the same latitude, is showing strain. Arctic melts. For most of recorded history, the Arctic Ocean has been covered by sea ice through every summer. The thick multi-year ice extended in winter to cover the entire ocean and shrank in summer to a remaining cap several million square kilometers in size. Satellite records, which began in 1979, have tracked a steady decline. The extent at the September minimum has dropped by more than 40%. The remaining ice is thinner and younger, with less multi-year ice every season. Climate models have for years predicted that the Arctic will eventually experience its first ice-free summer, defined as a year when sea ice extent falls below 1 million square kilometers in September. Older models place the event late in this century. Newer models, calibrated against the rapid decline already observed, place it much sooner. Some now project the first ice-free summer between 2030 and 2050, depending on assumptions and luck. The consequences extend beyond the polar region. Sea ice reflects sunlight back to space. Open ocean absorbs it. The change in reflectivity creates a feedback loop, accelerating local warming and pushing temperate weather patterns into unusual configurations. The atmospheric circulation that controls jet stream paths becomes less stable. Heat waves and cold snaps become more frequent in places far from the Arctic itself. For the first generation of humans alive when it happens, the symbolic moment will be sharp. The northern cap, which has shaped imagination since the first Ice Age maps were drawn, will simply not be there for a brief period each year. Polar bears, walruses, and many ice-dependent species will face habitat that no longer arrives on schedule. The Arctic will still freeze again in winter. But the year-round armour, the white crown on the world map, will have started to come off. Cascadia megaquake. Off the coast of the Pacific Northwest of the United States and Canada, the Juan de Fuca plate is slowly sliding beneath the North American plate. The boundary is called the Cascadia subduction zone. It runs for over 1,000 kilometers along the coast, from Northern California to British Columbia. Like its larger cousins in Japan, Alaska, and Sumatra, this kind of boundary produces some of the largest earthquakes the Earth is capable of. The last great Cascadia quake occurred at around 9 in the evening on the 26th of January in 1700. The date and time were reconstructed from Japanese tsunami records and ghost forests along the Oregon coast. The magnitude is estimated at around 9. The fault has been quiet since. Geological evidence shows that such quakes recur every 200 to 500 years on average, and the current interval is now over 300 years. When the next event arrives, it will release more energy than most people in the region have ever experienced. The shaking will last for several minutes. Coastal communities from Vancouver Island to Eureka will face a tsunami arriving within 20 to 30 minutes of the first shock. The seismic risk maps already identify thousands of buildings, bridges, and pipelines as critically vulnerable. Many of the structures that hold the modern Pacific Northwest in place predate the modern understanding of the threat. Estimates of casualties and economic damage from a full magnitude 9 event run into the tens of thousands and the hundreds of billions of dollars. Detailed planning exists in some jurisdictions and is nearly absent in others. The fault is loaded, the conditions are met. The only thing missing is the trigger, and the trigger does not announce itself in advance. New Island. The Hawaiian Islands are the visible tips of a chain of volcanoes that have erupted in sequence from a single hotspot in the Earth's mantle. As the Pacific tectonic plate slides north and west over the hotspot, new volcanoes form at the leading edge, while older volcanoes drift away, slowly subsiding into the sea. The active hotspot today sits beneath the big island of Hawaii, where Mauna Loa and Kilauea continue to erupt. About 30 kilometers southeast of the big island, beneath nearly a kilometer of seawater, the next Hawaiian island is rising. It was named Loihi when it was first identified as an active submarine volcano in 1952. The name was changed in 2021 to Kamehameha, the original Hawaiian name. The seamount stands over 3,000 meters above the surrounding seafloor and has erupted multiple times in recent decades, each event adding new lava to its summit. At its current rate of growth, Kamehameha will not break the surface for somewhere between 10,000 and 100,000 years. The estimate depends on how often eruptions occur and how much material each adds. The growth is real, the geology is well documented, and the future island is already being shaped beneath the waves. People standing in modern Hilo cannot see it. The mountain is there nonetheless. When the new island eventually emerges, the Hawaiian chain will have a southernmost member that did not exist when the islands were first settled by Polynesian voyagers around 1,500 years ago. The Big Island, the current youngest of the visible chain, will by then have drifted further north and started to slowly subside. The chain rolls onward, one new mountain at a time, building a small archipelago across the slowly turning ocean floor. Venus transit. A transit of Venus occurs when the planet passes directly between the Earth and the Sun, appearing as a small dark dot crossing the solar disk over several hours. The geometry is rare. Because the orbits of Earth and Venus are slightly tilted with respect to each other, transits happen in pairs separated by 8 years, and each pair is followed by a gap of either 105.5 or 121.5 years. The last pair of transits occurred in 2004 and 2012. The 2012 event was the most widely observed transit in history, watched live by millions through filtered telescopes and broadcast online from observatories around the world. Anyone who saw it then witnessed an event that nobody alive today will see twice. The next transit will not occur until the 11th of December in 2117. That date is roughly 90 years from now. The youngest viewers of the 2012 transit, infants at the time, will be over a century old. Modern medicine could conceivably push some of them into the year 2117, but the probability is vanishingly small. The next pair of transits will be witnessed by people not yet born, and most of them will not realize the event is unusual. Historical transits shape science in deep ways. Edmund Halley proposed in 1716 that careful observation of transits from multiple Earth locations would allow astronomers to calculate the distance from the Earth to the Sun, a measurement that anchored the scale of the entire solar system. The 17th and 18th century expeditions to observe transits were the first global scientific cooperations. The next transit will arrive in a world none of us can see. Millennium Clock. In the late 1990s, a group called the Long Now Foundation began designing a mechanical clock intended to keep time for 10,000 years. The project was led by Danny Hillis, an American computer scientist who had argued that modern civilization lived too much in the immediate present and needed concrete reminders of long timescales. The clock would tick once a year, chime once a century, and play a unique sequence of notes once a millennium. The first major prototype was completed in 1999 and ran briefly in a museum in London. A full-scale clock is now under construction inside a mountain in West Texas, on land donated by the Amazon founder Jeff Bezos, who has provided much of the funding. The mechanism is built from materials chosen for long durability, including titanium, ceramic, and stone. Power is drawn from temperature differences in the surrounding rock and from human visitors who wind the timing arm. The clock has no internet connection, no electronics, no batteries. The only access is by climbing a long shaft cut into the mountain. Visitors will reach a chamber holding the chiming mechanism, designed to ring a different combination of bells every 1,000 years, never repeating in the clock's expected life. The clock has not yet started running. Construction has been underway for years and is expected to continue for some time. If completed, the clock will be the slowest functional timekeeping machine ever built. Its first millennium chime is intended to ring in the year 3000, a moment that almost certainly no current reader will witness. The clock is a deliberate provocation, a piece of working hardware that demands its owners think across timescales that humans normally avoid. Its purpose is partly to keep time, and partly to remind anyone who sees it that time is much longer than they instinctively believe. Sealed vault. In 1936, the president of Oglethorpe University in Atlanta, Georgia, ordered the construction of an unusual storage room. The crypt of civilization was sealed in 1940 in a basement of the university and was not to be opened until the year 8113. The date was chosen as a span of 6,173 years from the sealing, matching the duration from the first known written records of antiquity to the moment of sealing. The crypt is a small stainless steel lined chamber. Inside are roughly 600 items intended to communicate the state of modern civilization to whatever inheritors find it. There are recordings of speeches by Adolf Hitler, Franklin Roosevelt, and the popular singers of the day. There are millions of pages of microfilm, sample dental floss, an electric toaster, a Donald Duck doll, a copy of Gone with the Wind, and a beer can. A windmill at the entrance was meant to generate power for the future inheritors to play the recordings. The door is welded shut. The instructions on the outer wall, intended to be readable for thousands of years, warn that the crypt must not be opened before the appointed date. The university maintains the chamber and the records of its contents. The exact way in which the contents will be read, given that modern playback equipment will probably not exist in the year 8000, is left to future ingenuity. The crypt is the oldest formal time capsule of this kind still sealed. Several others have been buried with longer wait times, including capsules planned for 100,000 years. The chamber in Atlanta is sitting quietly, year after year, holding a snapshot of mid-20th century American life behind a door designed to outlast the United States as a country. Green Sahara. The Sahara Desert today covers an area larger than the continental United States, with vast tracts of sand, exposed rock, and little surface water. The land was not always like this. Repeated cycles of climate over the last several 100,000 years have switched the region between wet and dry phases. The most recent wet phase, the so-called African humid period, ran from about 14,000 to 5,000 years ago. During that time, the Sahara was a grassland with lakes, rivers, and human settlements. Archaeological evidence from the period is dramatic. Rock paintings across the central Sahara show crocodiles, hippos, fish, and people herding cattle in landscapes that today are bone dry. The lake that once filled the Chad Basin was larger than any current lake on Earth. The Nile Delta was fed by rivers from regions that have not held running water in millennia. Then, around 5,000 years ago, the rains pulled south and the desert returned. The cycle is driven by slow changes in the tilt and wobble of the Earth's axis. The same forces that turn the planet's wobble through long periods change the position of the summer monsoon rains. Roughly every 20,000 years, the wet phase returns. The next greening of the Sahara, based on the orbital forcing alone, is not due for about another 12 to 15,000 years. Human-caused climate change may shift the timing. Some models suggest that increased moisture transport from a warmer atmosphere could speed up the return, possibly bringing partial greening within centuries instead of millennia. The data is uncertain. What is not uncertain is the long cycle itself. The Sahara will not always be a desert. The lakes will return, the herds will return, the rains will arrive again, on a calendar that does not consult anyone alive. Arecibo signal. On the 16th of November in 1974, the Arecibo radio telescope in Puerto Rico beamed a deliberate message into space. The signal was directed toward the globular star cluster M13 in the constellation Hercules, about 25,000 light-years away. The transmission lasted about 3 minutes. It was the most powerful signal humans had ever sent into space. The message was a sequence of 1,679 binary digits, designed by the astronomers Frank Drake and Carl Sagan to be readable as a two-dimensional image. It contained the numbers from 1 to 10 in binary. the atomic numbers of elements important to life, the chemical formula for DNA, a representation of the structure of the double helix, a stick figure of a human, the diameter of the radio telescope, a diagram of the solar system, and a sketch of the telescope itself. The signal will arrive at M13 in approximately the year 27,000. By then, the star cluster will have moved due to its own orbital motion, but the beam was wide enough that the signal will still wash over it. Any reply, even if it were sent immediately, would take another 25,000 years to reach the Earth. The earliest possible response, in the best case, would arrive around the year 52,000. The message has been criticized as premature and as scientifically more symbolic than meaningful. Whether the choice was wise or not, the signal is permanent now. The photons are traveling at the speed of light and cannot be recalled. Whoever or whatever the cluster contains in 25,000 years will receive a postcard from a civilization that by then may be unrecognizable or extinct. The bottle is in the cosmic ocean. Niagara stops. Niagara Falls, on the border between the United States and Canada, was carved by the Niagara River as it cut backward through soft shale and limestone toward Lake Erie. The cliff face has been retreating since the last ice age, when meltwater first established the river. The retreat is fast by geological standards. Over the last 12,000 years, the falls have moved upstream by about 11 kilometers. The current rate of erosion is about 1 foot per year on the American side and slightly more on the Canadian Horseshoe Falls. At that pace, the falls will continue to migrate south toward Lake Erie. Over the next several thousand years, the cliff will retreat past the original outlet of the lake. The Niagara River will then have a much smaller drop, or perhaps no drop at all, and the falls as a distinct landform will be gone. The full erosion will probably take 50,000 years. By then, the river will simply flow from one lake level to the next without the dramatic plunge. Tourists in the future will visit a flat river instead of a wall of water. The retreating gorge already shows the path the falls have taken, a long winding canyon stretching from their current position back to Lewiston, near Lake Ontario. In the meantime, water diversions for hydroelectric power already reduce the flow over the falls during overnight hours. The river has been engineered to keep the falls looking impressive during the day, while large amounts of water are routed through power stations behind the scenes. The natural landform is, in effect, on a long timer. Niagara, as a thunderous waterfall, is a temporary feature of the most recent geological era. Vega takes over. The Earth rotates around an axis that, today, points very nearly at the star Polaris in the constellation Ursa Minor. Polaris sits within 1 degree of true celestial north. Polynesian, Egyptian, Arab and modern European navigators have all used the star as a reliable indicator of direction. The axis of the Earth is not, however, fixed. It wobbles slowly under the gravitational influence of the Moon and the Sun, tracing a circle in the sky over a period of about 26,000 years. This wobble is called the precession of the equinoxes. As the axis traces its circle, different stars become the pole star at different times. 5,000 years ago, when the Egyptian pyramids were being built, the closest bright star to the celestial pole was Thuban, in the constellation Draco. Around the year 14,000 of the Common Era, the Earth's axis will point near Vega, in the constellation Lyra. Vega is the brightest star within the precession circle. When Vega becomes the pole star, the night sky will reorganize around it. Vega is a much brighter star than Polaris, and it sits at a higher elevation in the precession path. Navigators in that distant future will see a brilliant northern guide visible from a wider range of latitudes. The constellations themselves will not move much over that period, but their cultural meanings, tied for so long to a fixed Polaris, will shift in unfamiliar ways. The precession is too slow to notice within a human lifetime. Polaris will remain the practical pole star for centuries to come. But the slow tilt is real, the calendar is set, and the night sky is already drifting toward the configuration that Egyptians 5,000 years from now will think of as normal. The stars do not move. The Earth points elsewhere over time. Disappearing parts. The human body still carries the traces of features that were useful to ancestors and are now slowly fading. The appendix, a small pouch attached to the large intestine, was once a longer structure used in digesting tough plant material. In modern humans, the structure is largely vestigial and can be removed surgically with no obvious consequence. Evolution is gradually shrinking it. In some individuals, it is now nearly absent. Wisdom teeth, the third set of molars, were useful to ancestors with larger jaws who chewed harder foods for longer. Modern jaws are smaller. The teeth often have no room to erupt properly and require extraction. A significant fraction of people today are now born without one or more wisdom teeth, a small but measurable shift in human anatomy that has happened within a few hundred generations. The trend is continuing. The palmaris longus muscle, a thin tendon visible on the inside of the wrist when the thumb and little finger are pinched together, is missing in around 14% of people today. The muscle was likely used for climbing in tree-dwelling ancestors. Other examples include the plantaris muscle in the lower leg, the auricular muscles around the ear that allow some people to wiggle their ears, and the third eyelid, which survives only as a small pink fold in the inner corner of the modern human eye. Evolution is not a directed process. It removes structures only when their absence does not measurably reduce reproductive success. The slow disappearance of these features is invisible in any single lifetime. Over thousands of generations, however, the changes accumulate. The bodies of people born in 20,000 years will be subtly different from ours, with parts we still carry today that they no longer need at all. Voyager arrives. Voyager 1 was launched in 1977 and is now the farthest human-made object from the Earth. The spacecraft passed beyond the heliopause in 2012, entering interstellar space, and continues to send back faint signals as its plutonium power source slowly decays. By the late 2030s, the energy will be too low to operate the transmitter, and Voyager 1 will go silent. The craft will continue to move. Its current speed, around 17 kilometers per second, will carry it on a trajectory that, in roughly 40,000 years, will bring it within 1.5 light years of a small red dwarf star called Gliese 445 in the constellation Camelopardalis. The encounter is not a close pass by terrestrial standards. The probe will simply be in the same general region of the galaxy at the same time. Onboard Voyager 1 is a gold-plated phonograph record carrying greetings in 55 languages, recordings of music from around the world, and images of life on Earth. The Golden Record was designed by a committee chaired by Carl Sagan to communicate, in the unlikely event of recovery, some sense of the civilization that built and sent the craft. The record was meant to last at least 1 billion years against the slow erosion of cosmic dust. By the time Voyager 1 reaches the vicinity of Gliese 445, the civilization that built it will probably no longer exist in any recognizable form. The Earth itself will be a different place. The record will continue to drift slowly through the galaxy, carrying a snapshot of the late 20th century, on a journey calculated in millions of years. The chance of anyone ever finding it is incredibly small. Constellations dissolve. The familiar constellations of the night sky, the patterns named by ancient astronomers and used in modern star charts, are not fixed. They appear constant only because the stars they contain are so far away, and the relative motions of those stars are so slow that change is imperceptible within a single human lifetime. Over very long periods, the constellations slowly come apart. Each star in a constellation moves through the galaxy on its own orbit around the galactic center. Most of the bright stars in the night sky are at different distances from us and traveling in different directions. The Big Dipper, for example, contains 7 bright stars, of which 5 are members of a single moving group and 2 are passing through. Over the next 100,000 years, the 2 will drift apart from the 5, and the familiar saucepan shape will distort and break. 100,000 years from now, almost every traditional constellation will be unrecognizable. Orion's belt will no longer line up. The Southern Cross will tilt out of shape. The Pleiades cluster, which today appears as a tight knot of stars in Taurus, will scatter across a wider patch of sky. The patterns that have appeared in myths, navigation manuals, and zodiacal traditions for thousands of years are slowly walking apart. Future humans, if any are still here to look up, will see a different night sky. New patterns will form by chance as different stars drift into new alignments. The constellations have always been creatures of perspective, not of physical reality. The stars themselves do not care. The lines we draw between them slowly stretch, the patterns slowly dissolve, and the cultural memory tied to them will fade with them. Plastic layer. Future geologists, examining the rocks of the early 21st century, will encounter something new. The sedimentary layer being deposited today contains an unusual marker, a thin band of human-made polymer that did not exist on Earth before the 1950s. Plastic is now produced at a rate of over 400 million tons per year. A substantial fraction of it ends up in lakes, oceans, and river systems, where it accumulates in the sediment. Geologists already have a name for the proposed boundary that this layer marks. The Anthropocene is a proposed new geological epoch characterized by human activity. The plastic in modern sediment is one of several candidate markers, alongside aluminium fragments, radioactive isotopes from mid-20th century atomic tests, and concrete fragments from urban development. The layer can be detected from microscopic analysis of cores taken from lake beds and ocean floors. Plastic degrades slowly. In the cold, dark conditions of deep sediment, it can persist for millions of years. The layer will harden into a distinctive band of polymer-rich rock, marked by tiny fragments of bottles, packaging, and synthetic fibers. Anyone reading the rocks 10 million years from now will see a clear horizon, far thinner than the layers of normal sediment around it, separating the world before from the world after. Some of the largest specific markers will be especially durable. Plastic bottle caps, microbeads from cosmetics, and synthetic clothing fibers are all expected to survive, in recognizable form, on extremely long timescales. Future paleontologists may find them the way today's paleontologists find dinosaur teeth. The signature of our civilization in the rock will be a thin line of plastic. Eternal satellite. In 1976, NASA and the Italian Space Agency launched a small, unusual satellite into a high circular orbit. LAGEOS, short for Laser Geodynamic Satellite, is a brass sphere about 60 centimeters across, covered with 426 retroreflectors that bounce laser beams back to ground stations. It has no power source No electronics, no moving parts. It is simply a precise target, used for decades to measure the shape of the Earth and the motion of tectonic plates. The orbit was chosen carefully. At an altitude of around 6,000 kilometers, the satellite is high enough to avoid atmospheric drag and most space debris, and low enough to be tracked by ground-based lasers. Without atmospheric resistance, the orbit is expected to remain stable for an extraordinarily long time. The satellite is projected to remain in space for about 8.4 million years. Anticipating this future, the designers attached a small plaque to the satellite. The plaque is a kind of time capsule for whoever or whatever might recover Lagios when its orbit eventually decays. The plaque shows 3 maps of the Earth. One shows the configuration of the continents 225 million years ago. One shows the present. The third shows the predicted configuration 8 million years in the future, including the closed Mediterranean and the new Atlantic. The intended audience is unclear. The plaque is not a message for any specific civilization. It is a quiet statement that the satellite was meant to be found, perhaps by no one, perhaps by future humans, perhaps by something else entirely. Lagios still orbits today, still bouncing laser beams back to the ground, on a trajectory that has barely changed since the 1970s. The satellite will outlive almost everything any human has ever built. Mars rings. Phobos is the larger and innermost of the 2 moons of Mars. It is a small, irregular body, about 22 kilometers across, orbiting only 6,000 kilometers above the Martian surface. The orbit is unusually close. Phobos completes a full circuit in just 7 hours and 39 minutes, faster than Mars itself rotates. From the surface of Mars, the moon rises in the west and sets in the east twice a day. The closeness of the orbit is the source of Phobos's problem. The same tidal forces that slow Earth's rotation are pulling Phobos closer to Mars. Each century, the moon descends by about 2 meters. The descent is slow but steady. Within the next 30 to 50 million years, Phobos will reach a critical distance called the Roche limit, where the tidal forces overcome the moon's own gravity. At that point, the moon will start to break apart. The pieces will not fall to the planet directly. Instead, they will spread along the orbit and form a temporary ring system around Mars. For a few tens of millions of years, the red planet will have a thin set of rings, perhaps visible from Earth with a telescope. The rings will not be permanent. They will slowly fall to the Martian surface over time, peppering the equatorial regions with a long band of fresh craters. The event will be the most dramatic change in the appearance of Mars since the impact that created the Borealis Basin in the planet's northern hemisphere. The rings will give Mars, briefly by geological standards, a profile more like Saturn than the bare planet humans see today. By the time Phobos finishes its descent, the inner solar system will be quietly more decorative than it has been for billions of years. Mediterranean erased. The Mediterranean Sea sits between the European and African tectonic plates, in a region where the two are slowly colliding. Africa is being pushed north at a rate of about 2 centimeters per year, and the floor of the Mediterranean is being squeezed and folded as the gap closes. The current sea is the remnant of a much larger ancient ocean, the Tethys, which once stretched between the supercontinents Laurasia and Gondwana. The collision has been narrowing it for over 200 million years. The process will continue. In about 5 to 10 million years, the Strait of Gibraltar will close, cutting the Mediterranean off from the Atlantic. With no inflow to replace evaporation, the sea will dry, just as it did during the Messinian salinity crisis of 5.5 million years ago. The salinity crisis left a layer of evaporate salts beneath the current sea floor. that is over a kilometre thick in places. The drying happened in less than 1 million years. In the longer run, beyond the simple drying, the basin itself will close. The northward push of Africa will lift up huge mountain ranges where the sea used to be, similar to the way the collision of India with Asia produced the Himalayas. Modern Italy and Greece will be crushed against southern France and the Balkans. The space that the Mediterranean now occupies will become a vast new range of peaks, with cities buried under thousands of meters of new rock. The clear blue water visible today from Marseille, Naples, Athens, and Tel Aviv is a temporary feature. Over the scale of tens of millions of years, the entire Mediterranean basin will be folded into a chain of mountains. The civilizations that built around its shores will be gone long before that. The sea itself, in its turn, will be erased. Saturn unrings. The rings of Saturn are the most recognizable feature in the solar system. They consist of trillions of small particles of water ice, ranging from microscopic grains to bus-sized chunks, all orbiting the planet in a thin disk, less than a kilometre thick. The rings stretch over 280,000 kilometres across, more than 7 times the diameter of the Earth. Yet they contain only a small fraction of the Moon's worth of total mass. The rings are young. Analysis from the Cassini spacecraft, which orbited Saturn for over a decade ending in 2017, found that the rings probably formed within the last 100 million years. Their brightness, their composition, and the small amount of cosmic dust they have accumulated all point to a recent origin. Before the rings existed, Saturn looked like Jupiter, with no visible ring system to speak of. The rings are also temporary. Cassini measurements showed that material from the rings is steadily raining down onto the planet, pulled in by Saturn's gravity. The rate of loss is significant. At current rates, the rings will be substantially gone in about 100 million years, perhaps less. The water ice that makes them so bright is steadily falling toward the planet, where it adds to Saturn's atmosphere as a thin, invisible rain. By the time the rings disappear, the planet will look very different. The eye-catching halo that gives Saturn its identity in modern astronomy textbooks will be a thing of the deep past. Saturn will return to being a featureless gas giant, perhaps with a few thin remnant rings of dust. The brief window in which the planet has the most dramatic decoration in the solar system is, geologically speaking, almost over. Last eclipse. Total solar eclipses occur when the Moon passes exactly between the Earth and the Sun and is just close enough in size to fully cover the solar disk. The geometry is a coincidence. The Sun is about 400 times wider than the Moon and also about 400 times farther away. The two ratios match, which makes the Moon and Sun appear nearly the same size in the sky. The match is not permanent. The Moon is slowly drifting away from the Earth by about 3.8 centimeters per year, pulled outward by the same tidal interactions that slow the Earth's rotation. Over time, the Moon will become too far from us to fully cover the Sun. Eventually, every solar eclipse will be an annular eclipse, with a ring of sunlight visible around the Moon. The total disappearance of the Sun behind the Moon, which is the most spectacular feature of an eclipse, will no longer happen. The transition will be gradual. Total eclipses will become rarer and shorter over the next few 100 million years. The last total solar eclipse visible from Earth will occur in about 600 million years from now, in a specific location that future astronomers will be able to calculate precisely. After that, the disk of the Moon will simply be too small to fully cover the disk of the Sun ever again. This is one of the strangest facts about the modern epoch. The brief window in which the Moon and Sun appear exactly the same size is happening now, and humans, who developed eyes and curiosity precisely during this window, are the only species to have noticed it. There was a time when total eclipses did not happen, and there will be a time when they cannot. Pangaea returns. About 330 million years ago, all the continents of the Earth were joined into a single landmass called Pangaea. The continents had drifted together over hundreds of millions of years and would continue to drift apart over the following hundreds of millions. The breakup of Pangaea, beginning around 200 million years ago, produced the modern arrangement of continents and ocean basins. The continents are still moving. The geological forces that broke Pangaea apart are the same forces that will eventually push the continents back together. Models of plate motion, projected forward, predict that a new supercontinent will form within the next 200 to 300 million years. The exact shape depends on which assumptions are used. Several plausible futures have been proposed, including one called Pangaea Proxima, with all the continents collected around a central ocean. In the Pangaea Proxima scenario, the Atlantic Ocean stops widening and begins to close. The Americas drift back toward Europe and Africa. Australia moves north into Eastern Asia. Antarctica eventually rejoins the cluster from the south. The new supercontinent will span much of the globe, with a single vast ocean covering the other side. The interior of the landmass will be arid, far from any coastline. Whatever life exists on Earth then will face a fundamentally different climate. The vast interior deserts that defined Pangaea will likely return. Coastal areas, where most life concentrates, will be limited to the edges of the new continent. The cycle has played out at least 3 times before in Earth's history. Other supercontinents, called Rodinia and Columbia, came before Pangaea, each lasting a few hundred million years before drifting apart. The continents, like dancers in a slow waltz, are due to come together again. Plants suffocate. The sun is gradually growing brighter as it burns through its hydrogen fuel. Over the next 600 million to a billion years, the increase in solar output will heat the Earth significantly. Long before the planet becomes uninhabitable in any general sense, the increased temperatures will trigger faster weathering of silicate rocks. The chemical reactions that break down rocks at the surface pull carbon dioxide from the atmosphere. Plants depend on carbon dioxide for photosynthesis. Most modern plants use a photosynthetic pathway called C3, which becomes inefficient when atmospheric carbon dioxide drops below about 150 parts per million. The current concentration is around 420 parts per million. As the weathering accelerates with rising temperatures, carbon dioxide will be pulled from the atmosphere faster than volcanoes can replace it. In about 600 million years, the carbon dioxide level may drop below the threshold for C3 photosynthesis. The dominant trees, grasses, and crops of the modern world will no longer be able to grow. A smaller group of plants, including grasses that use the C4 pathway, can survive at lower carbon dioxide levels. They will persist for longer. Eventually, even those plants will reach their limits. The consequences cascade. Plants form the base of most food chains. As they fail, animals that eat them fail too. The oxygen content of the atmosphere, replenished by plant photosynthesis, will slowly drop. Within roughly 1 billion years, the surface of the Earth may be largely sterilized by suffocation and heat, long before the sun reaches the truly catastrophic stages of its expansion. The biosphere will end not in fire, but in the gradual loss of the air it depends on. Oceans boil. Around 1 billion years from now, the gradually brightening sun will have warmed the Earth enough to trigger a runaway process called the moist greenhouse. As surface temperatures climb above the current range, more water evaporates into the atmosphere. Water vapor itself is a powerful greenhouse gas. and the additional vapor traps more heat, raising temperatures further. The cycle accelerates. At some point, the atmosphere becomes so saturated with water vapor that the upper layers contain enough moisture to be broken apart by ultraviolet light from the sun. The water molecules split into hydrogen and oxygen. The hydrogen, the lighter component, escapes to space. Over the next several 100 million years, the Earth slowly loses its water through this process, dissolving into the void atom by atom. The oceans themselves will, at the same time, evaporate. The boiling point of water rises with atmospheric pressure, but the heat input from the sun will exceed the surface energy balance. The oceans will steam away, leaving wet beds of mud and dissolved minerals that gradually dry. The water cycle, which has shaped the planet for over 4 billion years, will simply stop. Earth will be a hot, parched world, similar in some ways to modern Venus. Most of life will be gone by then. The microbial life that may have hung on through earlier crises, including the suffocation of plants, will face conditions beyond what any cell can tolerate. The deep ocean refuges that have sheltered extremophiles since the very beginning of life will boil with everything else. The planet that produced humans will become, in the end, another lifeless world among the inner planets, no longer different from its neighbours. Neptune rings. Triton is the largest moon of Neptune. It has an unusual property among major moons. It orbits Neptune in the wrong direction, opposite to the planet's rotation. The retrograde orbit is strong evidence that Triton did not form alongside Neptune, but was captured from the Kuiper Belt, the population of small icy bodies in the outer solar system. Because Triton orbits backward, the tidal forces that normally raise satellites into higher orbits work the other way. Triton is gradually spiraling inward toward Neptune. Each million years, the orbit lowers slightly. Over the next several billion years, the Moon will move close enough to Neptune that tidal forces overcome its gravity, similar to the fate awaiting Phobos at Mars, but on a much larger scale. When Triton breaks apart, Neptune will gain a vast ring system. Triton is large, around 2,700 kilometers across, larger than Pluto. The pieces will form a ring much wider and denser than any in the modern solar system. For tens or hundreds of millions of years, Neptune will wear the most spectacular set of rings any planet has ever had. Viewers in the far future, if any are around, will see Neptune as a more decorated world than Saturn. Eventually the rings will fall to Neptune, just as Phobos will fall to Mars. The decoration is temporary. After the rings disperse, Neptune will be a featureless blue planet again, like Uranus, with a record of the lost moon, written only in the long, deep history of the outer solar system. Triton is, in a sense, already gone. It just does not know yet. Andromeda fills sky. The Milky Way galaxy is one of two large spirals in the local group, a small cluster of galaxies bound by mutual gravity. The other major member is the Andromeda galaxy, currently about 2.5 million light-years away. Andromeda is the most distant object that can be seen from Earth with the unaided eye, appearing as a small fuzzy patch in the autumn sky. The gap is closing. Andromeda and the Milky Way are moving toward each other at about 100 kilometers per second. In roughly 4 to 5 billion years, the two galaxies will collide. The encounter will not be like collisions in everyday life. Stars within galaxies are so far apart that individual stellar collisions will be vanishingly rare. The galaxies will pass through each other, their structures distorted by mutual gravity, and eventually merge. From the perspective of any observer on Earth or its descendants, the sky will change spectacularly. Over millions of years, Andromeda will grow larger and brighter, dominating the night sky. The familiar dim spiral will become an enormous luminous wheel covering much of the sky. After the collision, the two galaxies will be tangled together, with streams of stars and dust pulled into new arrangements. The final merged object, sometimes nicknamed Milkomeda, will be an elliptical galaxy without the spiral structure of either parent. The merger will not destroy life on Earth. By that point, however, the Sun will already be approaching the end of its main sequence life, and the Earth itself will be uninhabitable. The collision will play out for observers who, if they exist, will be on different planets around different stars. The Milky Way as we know it will have its final spectacular act in front of an audience we cannot send. Sun swallows Earth. In about 5 billion years, the Sun will have used most of the hydrogen in its core. The fusion of hydrogen into helium will move outward into a shell around the inactive core. The outer envelope of the Sun will expand and cool, turning into what astronomers call a red giant. At its largest, the Sun will reach a diameter that extends past the current orbit of Mars. Mercury and Venus will be engulfed in the early stages. Whether Earth survives is more uncertain. The expanding Sun will lose mass at the same time, which weakens its gravitational hold on the planets. The orbits of the surviving worlds may drift outward, possibly enough to keep Earth just beyond the Sun's surface. Even if it survives physically, the planet will be heated to thousands of degrees, the oceans long since boiled away. The red giant phase will last about 1 billion years. After that, the outer layers of the Sun will be cast off into space as a planetary nebula, leaving behind a small, dense white dwarf about the size of Earth. The white dwarf will radiate heat and shine faintly for trillions of years, slowly cooling. The planetary nebula will disperse within a few tens of thousands of years, leaving the white dwarf alone in the dark. Earth's fate is one of 3 outcomes: engulfment, where the planet falls into the expanding Sun and is vaporized; survival as a charred sphere, orbiting the white dwarf in an empty, cold, dark system; or destruction in a tidal interaction that breaks the planet into a ring of debris. None of the outcomes preserve any sign of the planet that birthed humans. The Sun, which has given Earth its light for billions of years, will be the agent of its end. Last star born, the universe is currently a productive place for new stars. Across the visible cosmos, galaxies form new stars from the gas and dust available in their interstellar medium. The total rate of star formation in the universe peaked about 10 billion years ago and has been gradually declining. The decline is not because new stars stop forming. It is because the supply of unused gas is being slowly used up. Stars need molecular clouds of hydrogen to form. As galaxies process more and more of their original gas into stars, the supply of fresh material runs lower. Stars themselves recycle some material when they die, returning gas to the interstellar medium through supernova and stellar winds. Each cycle, however, captures some material permanently into white dwarfs, neutron stars, and black holes. The total amount of free gas slowly drops. The very last new star in the universe will be born at some specific moment, in some specific galaxy, when the local gas supply is just enough to support one final collapse. Models predict this will happen in roughly 100 trillion years from now. By that point, the universe will be vastly older than it is today. Most galaxies will have stopped forming new stars long before. The last formation event will probably occur in a small, gas-rich dwarf galaxy. That final star will be small and dim, probably a red dwarf. After it lights, the universe will have no more new stars. The existing stars will continue to shine, gradually, for a long time afterward. Red dwarfs can burn for trillions of years, but the door of formation will be shut. Every star ever to exist in the universe will already be in the sky. The era of new stars, which has filled the cosmos with light for 13 billion years, will end on a specific night. Galaxies vanish, the universe is expanding, and the expansion is accelerating. Distant galaxies are receding from us, and the more distant they are, the faster they recede. This is driven by dark energy, the unknown force that fills empty space and pushes it apart. Over the past few billion years, the expansion has been speeding up, not slowing down. The implication for the future is dramatic. Eventually, distant galaxies will be receding from us faster than the speed of light. They will not technically violate Einstein's speed limit. Instead, the space between us will be growing faster than light can cross it. Once a galaxy crosses this cosmic horizon, no light from it will ever reach us again. The galaxy will, for all practical purposes, disappear. Over the next 100 billion to a trillion years, more and more of the universe will pass beyond this horizon. The local group, the cluster containing the Milky Way and Andromeda, is bound by mutual gravity and will stay together. Almost everything else will recede out of view. Future astronomers, looking out from any planet in the merged remains of the Milky Way and Andromeda, will see only their own galaxy and a few small companions. The rest of the universe will appear empty. The strangest aspect is that future observers will not know that other galaxies ever existed. The cosmic microwave background, the afterglow of the Big Bang, will eventually fade beyond detection. Without external galaxies to study, they will have no evidence of the expansion. They will conclude that the universe is small, static, and consists only of their cluster. The astonishing diversity of the visible cosmos today will be invisible to them. Last light, the last star to actually burn out, after the era of star formation has long ended, will be a small red dwarf. Red dwarfs burn so slowly that they can last for trillions of years, far longer than the current age of the universe. The smallest of them, with masses around 8% of the Sun's, are predicted to live for as long as 10 trillion years. After that, even they run out of fuel. When the final red dwarf exhausts its hydrogen, it does not explode. The star simply cools, contracts, and becomes a white dwarf, a dense ember radiating heat as it slowly chills. The transition is not dramatic. There is no flash. The star quietly stops being a star and becomes a remnant. For the universe as a whole, this transition will mark the end of stellar burning. The estimated date for this last shutdown is roughly 100 trillion years after the Big Bang, in the era astronomers sometimes call the degenerate era. By that time, the universe will be more than 7,000 times older than it is today. Every spiral galaxy will have collapsed into an elliptical. The merged remnants will contain only white dwarfs, neutron stars, and black holes, with no active stars producing new light. After the last red dwarf burns out, the only sources of energy in the universe will be the slowly cooling white dwarfs, occasional collisions, and the eventual evaporation of black holes. None of these are bright. The cosmos will fade into darkness, an immense, slowly cooling sea of dead remnants. The light show that has filled space since the first stars formed will be over. The constellation of every astronomer who ever lived will be ash. Black hole age. After the last stars burn out, the dominant objects in the universe will be black holes. These dense remains of dead stars and the supermassive black holes at the centers of galaxies will be the only places where the cosmos still has structure on a large scale. The era after the stars is sometimes called the black hole era, and it is expected to be far longer than every previous era combined. Black holes do not stay forever. The British physicist Stephen Hawking showed in 1974 that black holes emit a faint thermal radiation, now called Hawking radiation, that carries energy away from them slowly. The smaller the black hole, the faster it radiates. A black hole the mass of the Sun would take about 10 to the 67 years to fully evaporate, a number so large it has no physical comparison. Supermassive black holes take even longer. During the black hole era, the cold, dead white dwarfs and neutron stars will fall together or fall into black holes. Galaxies will continue to dissipate through gravitational interactions, with their remaining bound objects flung apart by chance encounters. The structure that has organized the visible universe since its formation will erode. By the very end of the black hole era, possibly 10 to the 100th power years after the Big Bang, even the largest black holes will have evaporated through Hawking radiation. The radiation itself is far below human detection limits and will become weaker still as the black holes shrink. The final evaporation of a typical supermassive black hole near the end of the era will release a tiny flash of energy that goes unwitnessed. There will be no observers left. The universe will be filled with extremely diffuse photons and elementary particles, and the era of any organized matter will be effectively over. Matter dies. Most current theories of fundamental physics predict that the proton, one of the basic building blocks of ordinary matter, is not perfectly stable. Over very long timescales, individual protons should decay, transforming into lighter particles such as positrons and pions. The predicted half-life is enormous, somewhere between 10 to the 34th and 10 to the 36th years, depending on the theory. Experimental searches for proton decay, conducted in deep underground detectors, have not yet observed the process. The detectors contain thousands of tons of pure water, surrounded by light sensors, that would register the energy released if a single proton inside the water broke apart. So far, none has been seen. The lack of detection rules out the fastest predicted decay rates, but is consistent with the slower ones. If protons do decay, then on cosmological timescales, all ordinary matter will eventually disappear. The atoms in stars, in planets, in dust, and in any preserved structures will gradually unmake themselves, one nucleon at a time. By the end of a long enough period, the universe will contain no protons, no neutrons, no atoms, only the elementary particles produced in the decay. The familiar building blocks of chemistry will be gone. For an extremely long stretch of cosmic future, the universe will hold the slow disappearance of matter itself. There will be no stars, no planets, no observers. Photons, neutrinos, and a few drifting particles will be all that remains. Whatever organized structure once existed, including the atoms that briefly assembled themselves into humans and stars and books, will dissolve back into the vacuum, particle by particle, on a timescale that makes the current age of the universe look like a single breath. Heat death. The universe is moving toward a state called maximum entropy. Entropy is a measure of disorder, or more precisely, of how evenly energy is distributed in a system. In a closed system, entropy can only increase. The Earth and the stars, the spiral galaxies, and the supernovae all represent local concentrations of low entropy, sustained by flows of energy that gradually even out over time. When entropy reaches its maximum, the universe arrives at a state called heat death. The name is slightly misleading. Heat death does not mean the universe gets hot. It means the universe becomes uniform, with the same temperature and the same density of particles everywhere. There are no longer any energy gradients to drive any process. No movement, no change, no event of any kind can happen. The cosmos becomes a vast, perfectly even, perfectly cold soup of nothing in particular. The timescale is so long that even the proton decay era is brief by comparison. After all the black holes have evaporated, after the last protons have broken apart, the universe will continue to expand. The remaining photons and neutrinos will spread out further. The temperature will approach absolute zero, but never quite reach it. Eventually, the wavelengths of the surviving particles will be longer than the distances between them. Heat death is, in the truest sense, the last event that will ever happen. After it, nothing happens. No further moments occur. The arrow of time, which has organized every event since the Big Bang, runs out of gradient. Time itself, if it still exists in any meaningful sense, becomes featureless. The story of the universe, from the first hot, dense moment to the last cold spread one, will simply have ended. There is nothing after.